Math 2414, Calculus 2, Calculus 1 Review. The chain rule, part 2. Find the derivatives, simplify your answers. You'll notice this picks up with D because in the previous video we did A, B, and C. We'll warn you this video might take a little bit longer than my videos normally run. I mean, just look at these problems. We have a quotient inside of a power. We have a product, but each product has powers, each factor has powers. We have a difference of two trig functions, which really isn't that bad. All right, so let's take a look at D. G of t equals t minus 2 over 2t plus 1, all raised to the 9th power. This is a pretty straightforward chain rule. It's just that when we get to the derivative of the inside, we'll have to execute the product rule. The hardest part about this one is not the calculus, it's the algebra. But for those of you who have gone through Calculus 1, you should already know that the hardest part about calculus is algebra and trigonometry. All right, so let's take the derivative. Who's on the outside of this function? The power. So we do the power rule and bring down the 9 and lower the power to 8 and leave the inside alone. Remember, that's part of the chain rule. Derivative of the outside, leave the inside alone, then derivative of the inside. But the inside of this is a quotient, which means we will have to use the quotient rule. So be very careful as you proceed forward. All right, quotient rule. A lot of ways to think about it, but either way, the denominator of the derivative is the square of the original denominator. In other words, square the bottom. And on the top, I'm going to use the Tibbet gimmick. And if you don't know what I mean by the Tibbet gimmick, go back and watch the first video in this series. The I really is an apostrophe meaning derivative of. All right, so derivative of the top, the derivative of t minus 2 is just 1 times the bottom, 2t plus 1, minus, let's clean that up, minus the derivative of the bottom, the derivative of 2t plus 1 is 2, times the top is t minus 2. All right, so the derivative is not going too terribly bad. We just got to clean this mess up as much as we can. So what can we do to clean it up? Well, obviously we need to clean up this numerator over here. But another thing that's a little bit more stealthy, but just as easy to clean up, is we have a lot of 2t plus 1s in the denominators, and we're going to expect those to be put together. So let's see what we get. Let's start making one big fraction. We got the 9 on top. This quotient raised to a power, we can give the power to each side. So t minus 2 to the 8th on top and 2t plus 1 to the 8th on the bottom. And then in the last part, the derivative of the inside, we have a 2t plus 1 squared. So this will give us a power of 10 on the bottom. And then we also have this cleanup. We'll do a little bit of distributing, but it's going to be pretty easy. Distributing 1 is kind of pointless, but if you must, 1 times 2t is 2t, and 1 times positive 1 is positive 1. And then here we would distribute a negative 2. Negative 2 times t is negative 2t, and then negative 2 times negative 2 is positive 4. Okay, this won't take too long to clean up. In that last factor, the 2t's cancel, leaving us 1 plus 4, which of course is 5. But now we have a factor of 5, which can multiply with this factor of 9 to give us a factor of 45. We have a t minus 2 to the 8th on the top. And on the bottom, we have a 2t plus 1 to the 8th times 2t plus 1 to the 2nd. So we can just add the exponents and get 2t plus 1 to the 10th. And in my opinion, this is the cleanest answer. Not just because we cleaned up this numerator, but because we combined all these common factors in the denominator. And in such a problem, I would expect you to clean it up similarly. Let's draw a partition line here. It's going to get a little bit crowded. Again, I said this before, and I should say it more often. You are always welcome and recommended to pause the video and see if you can work out some of the examples before I do. Yeah, I know that one's already done, but I invite you to do the same with both of these. So if you want to try h of x before I do, pause the video, give it a try, unpause, and here we go. All right, h of x is a product. 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. So let's invoke the product rule. Answer. Remember how the product rule goes. The derivative of the first times the second plus the first times the derivative of the second. For the derivative of the first, we'll have to invoke the chain rule because we have a power on the outside and a polynomial on the inside. So the derivative of the first will be bring down the power, lower the power by 1, and then leave the inside alone. Chain rule swoops in and says, don't forget me, times the derivative of the inside. The derivative of 2x plus 1 is just 2. But be careful because all of this that we've done so far is just the derivative of the first. We still have to multiply times the second. So derivative of the first times the second times x cubed minus x plus 1 to the fourth. It's going to run into that. I'll probably just move that over here after the problem because we still have to complete the product rule, which is the first times the derivative of the second. So plus the first, 2x plus 1 to the fifth, times the derivative of the second, and we'll have to invoke the chain rule again. So let's invoke the chain rule again. For the derivative of the second, the outside is a power, so do the power rule. Bring down the power, lower the power by 1, so it'll be cubed. And then leave the inside alone. X cubed minus x plus 1. And then times the derivative of the inside to complete the chain rule. The derivative of x cubed minus x plus 1, term by term, is 3x squared minus 1, and of course the derivative of the plus 1 is 0. All right, so at this point the calculus is over. It was a lot of calculus, product rule, power rule, chain rules, but the calculus is over. Now the rest is just cleaning this mess up. Now, how can we clean this up? Well, there's two ways to look at this, as pieces and as one whole. As pieces, it's a giant addition problem. This addend plus that addend. As a whole, it's one giant addition problem. So what I would recommend is cleaning up each half of the addition problem as much as you can and then looking at the problem as a whole. Now, what do I mean by clean up the addition, each half of the addition problem? Well, since each half is just a big product, I would look for things that I could put together. If you're thinking, do I want you to write out all these parentheses and fold them? Absolutely not. First half of the product, the first half of the addition problem is pretty easy to clean up. Let's put a green box around that since it's getting kind of congested up here. I've got 4 factors, this 5, this parentheses, that 2, and that parentheses, and the only 2 factors I can do anything with are the 5 and the 2. 5 times 2, of course, is 10. I can't do anything with the 2x plus 1 to the fourth, and I can't do anything with x cubed minus x plus 1 to the fourth. Well, I can write them out and multiply them, but I choose not to. You'll see why in a moment. Plus, and if we clean up the second half of this, I don't think there's really anything we can clean up. I guess we could distribute this 4 across here. You can't distribute it across here because of the power. Remember, please excuse my dear Aunt Sally, the exponent would have to occur before the multiplication. But I could commute this 4 over here and distribute it across there, but I don't see a benefit to that either. I think the only thing I'm going to do at this point is rewrite it with a constant in front and then just write all the factors. 2x plus 1 to the fifth, x cubed minus x plus 1 to the third, and then 3x squared minus 1. So it doesn't look like a whole lot happened. Really the only thing I did was multiply 5 times 2 and rearrange the way I write, the order in which I write some things. But now look at the problem globally. Not as 2 halves of an addition problem, but an entire addition problem. What happens next looks harder than it is. It's actually pretty easy. We're going to factor. We're going to factor out a common factor by looking at these 2 big chunky multiplication problems and seeing what they have in common. Let's start with the numbers. 10, 4. They have a 2 in common. We're going to factor that out. Is there anything else they have in common? Some 2x plus 1s. When you factor out a greatest common factor, the most you can factor out is determined by the lowest power. This guy has 4 of these parentheses, this guy has 5 of them, so the most I can take from them is just 4 of them. I'm going to factor 4 of the 2x plus 1s out of both factors. Out of both addends, excuse me. Is there anything else they have in common? The x cubed minus x plus 1s. But again, I can only factor out the lowest power from them, and that lowest power would be 3. So I'm going to factor out an x cubed minus x plus 1 all to the third power. Now that's just what I'm going to remove from everybody. Now I need to see what's left. I could write a giant parentheses, but I'm going to use some braces just so that it looks different. But it's really just a different symbol, meaning a grouping symbol. Let's see what's left over from each half of the addition problem when we factor out these guys. Factoring is just dividing. 2 goes into 10 5 times. If I factor out 4 of these 2x plus 1s, that's all it had. It loses them all. There are no more 2x plus 1s left over here. But I only factored out 3 of these parentheses, and it had 4, which means it will have one of those parentheses left over. That looks like I'm going to distribute it, and I will here in a moment. Plus, all right, let's do it again. 2 goes into 4 2 times. I take out 4 of these parentheses, but it had 5 of them, which means it will have one of them left over. I take out 3 of these parentheses, and it had precisely 3 of them, so it has none left over, but it does have this 3x squared minus 1. Now, is there a benefit to all this? Actually, yeah. Now that I've factored out what each half of the addition problem has in common, everything else over here can be busted open and combined like terms. I should be able to collapse this down quite a bit. The first parenthesis is pretty easy. I'm just going to distribute this. But the second one's going to take 2 moves because I have a FOIL problem and a distributive property problem. In a case like that, I usually FOIL it first. So we're going to FOIL that, and once we FOIL, we're going to distribute the 2 across it. All right, let's let this just percolate for a minute because it's not going to do anything. Let's see what happens over here. 5 times x cubed is 5x cubed. 5 times minus x is negative 5x. 5 times positive 1 is positive 5. That part was easy. Let's kind of FOIL this right here, and then we'll distribute the 2. The first part of FOIL is 2x times 3x squared, which is 6x cubed. The outside part is 2x times negative 1, which is negative 2x. The inside is positive 1 times 3x squared, which is positive 3x squared. And then the last part is positive 1 times negative 1, but that has a 2 in front of it, and more specifically a positive 2. And so if we distribute that, positive 2 times 6x cubed is positive 12x cubed. Positive 2 times negative 2x is negative 4x. Positive 2 times positive 3x squared is positive 6x squared. Positive 2 times negative 1 is negative 2. And now I just got a smattering of like terms to combine. And I think I'm about ready to write my final answer. Let's bring back these guys. They're just sitting there patiently, like hopefully you are. And let's gather them from highest to lowest terms. I'll circle terms and cross them out as I use them to make sure that everybody's accounted for. Highest power is x cubed, and it looks like we have 17 of those. So 17x cubed, we're done with those. Next highest power is x squared, and this is the only one I see. So positive 6x squared. Next to my x's, there's a minus 5x and a minus 4x, and that makes minus 9x. So those are done. And lastly is my constant terms. I have a positive 5 and a negative 2, which makes positive 3. And can this go any further? When's it ever going to stop? Well, the only thing that might happen, but it probably won't, is that this could factor further. But factoring this would require using the rational zero theorem and synthetic division. But for purposes of cleaning this up, I think this is good. This is a good stopping point. I've got it completely factored, and heaven forbid if I put this derivative equal to 0 and solve it, it actually wouldn't be that bad. Solve this equal to 0, I get negative 1/2. Solving this equal to 0 would require some techniques that are beyond this course, and then this might not even have any pretty answers either. So forget I ever went down that path. All right, oh, wait a minute. That was just E. That was E. Am I gonna expect you to take something like this and simplify it like that? If I do, I would only ask you to do it once on a homework assignment, and as a test question, well, we're just reviewing. This wouldn't even be on the test. But yeah, I mean, it's a nice algebraic cleanup. Let me see what time mark we're at right now. Well, I could stop and make one more video, but this last one's not going to take very long. So this is going to be one of the longer video in the series, I hope. And by the way, of course I'm filming these in order, so I don't know how long future videos will be. I try to keep them around the 10-minute mark. Sometimes they hit the 15-minute mark. On occasion they hit the 20-minute mark. Sometimes they're less than 10 minutes. But this is Calculus 2, so you should expect things to get ugly. All right, so let's hit this last one. It's kind of hidden inside of here. I'm going to move it over there. R of theta. And if you're wondering why am I using R, why am I using theta? Because at the end of this course we're going to get to polar coordinates, and one of the variables is an angle called theta. And in Calculus 3, you do represent things using stuff like R of theta. It's just another function. Secant squared of theta minus tangent squared of theta. And you might be thinking, well, this one doesn't look too terribly bad, and you would be right, but there's a reason I'm doing it. I challenge you to find its derivative, and you may be surprised by its result. All right, so let's find the derivative. Wait a second. Oh yeah, this does involve the chain rule. This involves the chain rule. Actually, before we take the derivative, I think I'm going to rewrite it as secant theta squared minus tangent theta squared, just to emphasize the outside and inside aspect of the chain rule. All right, r prime of theta. For the secant squared, we do the power rule, so bring down the power and lower it by 1. Leave the inside alone, but then the chain rule jumps in and says, not so fast, you're not done. Times the derivative of the inside. The derivative of secant theta is secant theta tangent theta minus, I'm going to get rid of this. Don't worry if you didn't write it down, you can always back the video up. All right, same thing over here. Power rule first, bring down the 2, lower the power to 1, leave the inside alone. Chain rule says times the derivative of the inside, the derivative of tangent is secant squared. I think the hardest part about this one is the cleanup, but you might be surprised how easy the cleanup is actually going to be. Just like in the previous example, we have a subtraction problem with 2 chunky halves. Let's see if we can clean them up a little bit. The left half of the subtraction problem, we have a 2. We have a tangent, only one of them. But we have a secant times a secant, and that makes a secant squared x. Secant squared theta. And I don't know why I wrote a square on this tangent. I must have been thinking too far ahead. But we have 2 tangent secant squared, and on the second half, there's really nothing to combine. We have a 2, a tangent, and a secant squared. Those match. We're subtracting. Their difference is 0, which makes you go, huh? The derivative is 0? That was unexpected. Or was it? The reason I did this last example wasn't just to show you another example of the chain rule. I mean, yeah, it used the chain rule. But the reason I did this last example is that sometimes it pays to think before you jump into a problem. Because if you're really on top of your trigonometry game, you might have recognized something. It's not F, it's R. You might have said, wait a second, secant squared theta minus tangent squared theta, isn't that some sort of Pythagorean identity? And the answer is sort of and yes. Because as a Pythagorean identity, it's usually written as 1 plus tangent squared theta is equal to secant squared theta. This is one of 3 Pythagorean identities. The other 2 are sine squared theta plus cosine squared theta equals 1, and 1 plus cotangent squared theta equals cosecant squared theta. You know, that trig stuff you should already know by Calculus 2. But if you recognize that this kind of looks like a trig identity, then I can take this identity and make a different version of it by moving the tangent over and get 1 equals secant squared theta minus tangent squared theta. In other words, this function is identical to 1, which makes its derivative really easy. Excuse me, I'm thinking Calculus 3 and wrote a vector over it. Therefore, the derivative of theta is the derivative of r of theta, which is the derivative of 1 is 0, and it's over. In general, anytime you take a derivative and get 0, that means the original function was actually a constant. It's a nice trick to have up your sleeve. To show something as a constant, you can show its derivative is equal to 0. All right, well, that was neat. All right, let's move on.